limits. The limiting process respects addition, subtraction, multiplication, and division as long as the limits and functions under consideration are well defined. Come, let's formalize these as a theorem. Number 1. Limit of sum of two functions is sum of the limits of the function, that is, limit x tending to a. fx plus gx equals limit of x tending to a. fx plus limit x tending to agx. Number 2. Limit of the difference of the two functions is the difference of the limit of the functions, that is, limit x tending to a. fx minus gx equals limit of x tending to a. fx minus limit x tending to a. gx. Number 3. Limit of product of two functions is the product of the limits of the function, that is, limit x tending to a. fx into gx equals limit of x tending to a. fx into limit x tending to agx. Number 4. Limit of quotient of two functions is quotient of the limit of the functions whenever the denominator is non-zero, that is, limit x tending to a. fx divided by gx equals limit of x tending to a. fx divided by limit x tending to a. gx. Note that, in particular, as a special case of a point number 3, when g is a constant function such that gx equals lambda. For some real number lambda, we have limit x tending to a. Lambda into fx equals lambda into limit x tending to a. fx. Limits of polynomials and rational functions. We know that limit x tending to a, x equals to a. Hence, limit x tending to a, x square equals to limit x tending to a. x into x, which equals to limit x tending to a. x into limit x tending to a. x, that is equal to a into a, which is finally equal to a square. An easy exercise in induction on n tells us that limit x tending to a, x raised to the power n equals to a to the power n. Now let fx equals to a naught plus ax plus a2 x square up to an to the power up to anx to the power n be a polynomial function. Thinking of each a0, a1x, a2x up to a1x to the power n as a function, we have limit x tending to afx equals to limit x tending to a0 plus a1x plus a2 x square up to anx to the power n equals limit x tending to a0 plus limit x tending to a1x plus limit x tending to a2x square up to limit x tending to an x to the power n. Now this is equal to a0 plus a1 limit x tending to x plus a2 limit x tending to x square up to an limit x tending to x to the power n. This can be written as a0 plus a1 a plus a2 a square up to an a raised to the power n. Now this is equal to f of a. A function is said to be a rational function if fx equals gx divided by hx, where gx and hx are polynomials such that hx is not equal to 0. Then limit x tending to afx equals limit x tending to agx divided by hx, that is equal to limit x tending to agx divided by limit x tending to ahx, which is finally equal to g, a divided by h, a. However, if ha equals to 0, there are two scenarios. 1. When ga not equals to 0, and second, when ga equals to 0. In the former case, we say that the limit does not exist. In the later case, we can write gx equals x minus a raised to the power k into g1x, where k is the maximum power of x minus a in gx. Similarly, hx equals to x minus a raised to the power k into h1x as ha equals to 0. Now, if k greater than I, then we have limit x tending to a. fx equals to limit x tending to a. gx divided by limit x tending to a. hx, which is equal to limit x tending to a, x minus a raised to the power k into g1x divided by limit x tending to a, x minus a raised to the power I into h1x, limit x tending to a, x minus a raised to the power k minus I into g1x divided by limit x tending to a, h1x equals to 0 into g1, a divided by h1, a, that is equal to 0. But if k is less than I, then the limit is not defined. Let's take an example. Find the following limits. Let's see the solution. The required limits are all limits of some polynomial functions. Hence, the limits are the values of the function at the prescribed points. We have number 1. Limit x tending to 1. X cube minus x square plus 1 equals 1 cube minus 1 square plus 1, which is equal to 1. Number 2. Limit x tending to 3. X into x plus 1 equals to 3 into 3 plus 1, that is equal to 3 into 4, which is equal to 12. Number 3. Limit x tending to minus 1. 1 plus x square up to x raised to the power 10. Putting the value of x as minus 1 and then simplifying the equation, we get the final answer as 1. Let's take an example. Find the following limits. All the functions under considerations are rational functions. Hence, we first evaluate these functions at the prescribed points. If this is of the form 0 by 0, we try to rewrite the function, cancelling the factors which are causing the limit to be of the form 0 by 0. Number 1. We have limit x tending to 1. X square plus 1 divided by x plus 100. Now putting the value of x equals to 1, we get the result as 2 by 101. Number 2. Evaluating the function at 2, it is of the form 0 by 0. Hence, limit x tending to 2, x cube minus 4x square plus 4x divided by x square minus 4 can be written as limit x tending to 2x into x minus 2 whole square divided by x plus 2 into x minus 2. Cancelling out the common terms and then putting x equals to 2, we get the final answer as 0. Number 3. Evaluating the function at 2, we find that it is also of the form 0 by 0. So, here again, we do the same thing as we had done in the problem number 2. That is, factorizing the numerator and denominator, cancelling out the common terms and then putting the value of x equals to 2. But then we find that the scene is a little different because the answer comes to be equal to 4 divided by 0, which is not defined. Number 4. Again we have the 0 by 0 form. Again we follow the same steps and get the final result as minus 4. Number 5. First, we rewrite the function as a rational function. That is, we take the LCM and then simplify to get the function as x squared minus 4x plus 3 divided by x into x minus 1 into x minus 2. Now, evaluating the function, we find that it is also of the 0 by 0 form. Hence, we follow the same steps that we have learned to deal with this type of problem, and finally we get the result as 2. We remark that we could cancel the term x minus 1 in the above evaluation because x not equal to 1. Evaluation of an important limit which will be used in the sequel is given as a theorem 2, which we are about to learn next. Theorem 2. For any positive integer n, limit x tending to a, x to the power n minus a to the power n divided by x minus a equals to n into a raised to the power n minus 1. Remark: the expression in the above theorem for the limit is true even if n is any rational number and a is positive. Now let's see the proof. Dividing x to the power n minus a to the power n by x minus a, we see that x to the power n minus a to the power n equals to x minus a into x to the power n minus 1 plus x to the power n minus 2 into a up to x into a to the power n minus 2 plus a to the power n minus 1, then putting x equals to a, and then simplifying it further, we get the result as n into a to the power n minus 1. Let's take an example. We have to evaluate the following limits. Solution. Number 1. We have limit x tending to 1, x to the power 15 minus 1 divided by x to the power 10 minus 1. Dividing x minus 1 from both the numerator and the denominator, then using the theorems learnt and then finally putting x equals to 1 followed by simplification, we get 15 divided by 10 equals to 3 by 2. Number 2. Put y equals to 1 plus x so that y tends to 1 as x tends to 0. Then the limit becomes limit y tends to 1 root y minus 1 divided by y minus 1. You will note that 1 in the numerator can also be written as 1 to the power half. So it gets reduced to a known form, and hence putting the value y equals to 1, the answer comes out as half.